In this video, I will talk about the buoyant force and I will show you how to use it. This is the expression that gives us the buoyant force, and this is the magnitude of the contact force, and this is because the contact force, the buoyant force, is truly a contact force. So this is the buoyant force. Let's fix this. So the left side is the buoyant force. It is a contact force because the buoyant force is the contact force that the fluid exerts on an object that may be either partially submerged or fully submerged in the fluid. So it is a contact force that the fluid exerts on an object. So this is for fluid. And I want to remind you, a fluid can be a liquid or a gas. And by O, I mean the object. And this is because the buoyant force is truly a contact force. Now, we are familiar with G, the constant 9.8 for the surface of the planet Earth. Now, M sub, I need to change this. This should be M sub F, the mass of the fluid displaced. So this M here, it is a mass. And it is the mass of the fluid that your object displaces. Now, how will you find the mass of the fluid that is displaced by your object? I'm going to show you what that means. When you have, let's say, when you have the entire box, the entire cube fully submerged in your fluid, then the amount of fluid that this cube displaces is the entire volume of the box. So in this case, let's call this, let's say this is case B. Let's call this case A. In case B, I will calculate the mass of the fluid displaced by saying, well, my cube is displacing its entire volume of fluid away. So I'm going to use the volume of the object, and I'm going to use the volume of the object that is fully submerged, but I need to multiply that with the density of the fluid. Okay, this is the entire volume of the object for case B, because in case B I have the cube, the object fully submerged, and this here is the density of the fluid. Now I want to talk a little bit about this. The reason why I'm using the volume of the object and the density of the fluid. Okay, this is important. What was in here, if I remove the box, if I take it away, it's gonna be filled with water. What I need to calculate here is the mass of the water that would have been here had this cube, if this cube was not occupying the space. How much space are we talking about? We're talking about the space equal to the volume of the object. Now, how can I find the mass of the water that would occupy this space? Well, I need to take this space, the volume of the object, multiplied with the density of the fluid, because this would be filled with water, and then the density times the volume will give me the mass of the fluid that I would have here had the object not taken its place. Now, in case A, you can see now my object, my cube, is not fully submerged. It is displacing some fluid away, but not as much as it did in case B. Now it is displacing, let's say, approximately half of the entire volume because I have it halfway submerged in the fluid. So how much, okay, if I take this cube in case A, if I take it away, how much fluid will occupy the space that my object occupies now? It will be this. It will be how much fluid you would have in this lower portion of the cube. Now, to find the mass of the fluid here, I need to know, first of all, the density of the fluid, as I did before, but I also need to know how much of the volume of the object is submerged. Now, if we say that it's halfway through, now I'm going to use the volume of the object divided by 2. And this is because here the object is not fully submerged. You only have that cube, you only have that object partially submerged in the fluid. Only part of it is inside in the fluid. So you will always be calculating the mass of the fluid displaced by using the density of the fluid, and you can see here I'm always using the density of the fluid. And then for volume, you need to use the volume of the object that occupies the space of fluid. If it is partially submerged, you will just use the portion, the volume of your object that is in the fluid. If it is fully submerged, of course, you have to use the entire volume. So this is how you will do the calculations. I want to remind you that when you do these calculations, you will be using G 9.8 meters per second squared. If you are dealing with water, the density of water is 1000 kilograms per meters cubed. And we can do a simple example. Let's say if I have, let's say that the volume, let's make this an example. If you have a cube that has a volume, the volume of the object, let's say 8.0 centimeters cubed, and if I convert this to meters cubed, it will be 8.0 times 10 to minus 6 meters cubed. And really quick, I want to show you how I did this conversion. 1 centimeter, I want to remind you how I do that, is equal to 10 to minus 2 meters. Now, if I raise everything to the power of 3, 1 cubed, centimeters cubed, 10 to minus 2 cubed will be meters cubed, then what you get is that 1 centimeter cubed is 10 to minus 6 meters cubed. All right, that was parenthesis, a side note. Now, if I have a cube that has a volume equal to 8 to 10 to minus 6 meters cubed, then I can calculate, if it is for case A, if I make it halfway through, then the buoyant force from the fluid on the object is F on the object. This will be the mass of the fluid displaced, which will be the density of my fluid. So case A, I'm here. The density of water is 1000. and I have the volume of the fluid displaced. It is half of the volume of the object. Now this will give me the mass of the fluid displaced, and then don't forget to multiply this with 9.8. Okay, this will be, don't forget, this will be in newtons. This will give you the buoyant force that the fluid exerts in this case. Now in case B, the magnitude of the buoyant force that the fluid will exert on the object is the density of the fluid, which is the density of water. Since it is fully submerged, now I need to use the entire volume, and then of course I need to multiply that with the constant 9.8, and this will also be in newtons. Now I do want you to compare these two results. The second one, in case B, you will have the buoyant force will be twice as large. Now what's the reason for this? Here you have the entire volume of the object submerged, so here the fluid is pushing on the cube upwards with a greater force than what it does here. Okay. And as a final note, do remember that the buoyant force is always pushing the object upwards. So this is the direction of the contact force the fluid exerts on the object. And similarly here, now this contact force, the buoyant force, will be twice as large. So let's do this. This will be the buoyant force in the second case. It will be greater in magnitude because now the object is fully submerged. So the calculations in general for the buoyant force are fairly simple, but you do need to be careful with how much volume of the object is submerged in the fluid.